Welcome to Chemistry at Honega High School. I'm Brian Brown, and today we'll be looking at the first section of Chapter 4 in our Day 1 notes. And Chapter 4 deals with understanding atomic structure. And this is another core chapter that end up using in other chapters later on. Now, our earliest models, or our earliest way of looking at the world around us, go back to the ancient Greek philosophers. Do you recognize either of these names, Aristotle or Democritus, or Democritus, depending on how you want to pronounce it? Well, most people recognize Aristotle, and unless you've talked about democracy and the concept and where it came from, you may not have heard of Democritus. And that has some implications in terms of science and chemistry and understanding. Now, one of the earliest models of, and calling it atomic theory is being nice because it's really not a theory, because it doesn't explain chemical behaviors all that much in terms of chemical interactions, and it also isn't based upon empirical or scientific evidence. So it's really more of the idea of the atom. But the idea of the atom actually goes back to ancient Greek times, where Democritus said that matter is composed of empty space through which atomos move. Now, that's where we get the term atom, and atomos stands for indivisible particle. So what he said was the world around us is made up of these little indivisible particles. And atoms were then small indivisible particles whose shape determine the properties of matter. So something like water. Well, water is bluish in color when you look at a large amount of it, and it flows really, really easily. So what he said was, well, that must mean water's atoms, which were the incredibly, incredibly small things, too small to see, but collectively we could see them, must be these round little spheres of light blue color that slide past each other very easily. Whereas something like iron, which is very hard and durable, they must be made up of these little spiky gray atoms that clump together and stick really hard to each other. And this was his view of how the world existed. Now, no, he wasn't right, but at least he had a kernel of an idea that was going to lay buried for thousands of years, because one of the greatest thinkers of the day was Aristotle. And he believed in something very different. So he didn't believe in the atomic, discontinuous way of looking at things. He believed in the elemental theory, where everything was continuous and tied together, and everything was in the world was made up of combinations of fundamentally four elements: earth, fire, water, and air. And there's more to the theory, but the reality is he was way off base, but he was a genius. And between the two, who are you going to believe? The one that is the accepted genius or not? So what really happened was Aristotle won. His viewpoint dominated. And because he was considered one of the greatest thinkers of his time, really it set us back thousands of years in science and in chemistry, because we spent a lot of time looking at things through a very, very inaccurate lens. And it wasn't until the time of Dalton in the 17 and 1800s that atomic theory was really revitalized. Now, other people had been coming back to this idea in this time frame, but Dalton was the first person to put these ideas together in a true atomic theory. So this is our first real theory of the atom, because it explains behavior of interactions of particles, and it also is based upon experimental evidence. Now, he said atoms are small, solid, indivisible particles. Sounds pretty much the same so far. Different elements are made up of different atoms, but atoms of the same element are identical. That's also similar to what was looked at before. But a major difference was many of the things that somebody like uh, Democritus was calling an atom or was calling an elemental substance was actually a compound or even a mixture of many different types of pure substances. And by Dalton's day, we had a better list. No means complete, and yes, there were still inaccuracies on our list of elements, but we were much more farther along in our understanding of elemental substances. Third thing, atoms combine in simple whole number ratios to make compounds. He's describing how and why chemical reactions are occurring. And in a reaction, atoms are rearranged, which goes to the idea of not creating or destroying atom. All you're really doing is taking these little building blocks and rearranging them. Now, are any of these ideas believed to be incorrect today? Well, it shouldn't be a surprise that as science advanced and technology advanced, we discovered some things that we had no way of knowing was true back at this time frame. First thing would be really the first one, solid indivisible particles. We know atoms are anything but solid. Most of an atom is actually empty space. And it's not indivisible in nuclear reactions, which happen spontaneously all the time around us. It's just not to a great degree, so we don't notice as much. Particles of atoms do break in nuclear reactions, in unstable radioactive decays. Yes, atoms do actually spontaneously break apart. And in collision reactions, we can actually make atoms break apart. So we know they're not indivisible particles. We also know that atoms of the same element are actually not identical to each other nowadays. And once again, we couldn't see the atom, we couldn't see into the atom. It took us a while to come up with evidence that showed that not all carbon atoms were exactly alike. Chemically, yes, they behave the same way, but physically they're a little bit different. Now, one of the things you need to have a better understanding about the atom is really its relative size. So, how big are atoms? Well, they're really small. And when I say really, I mean really small. Honestly, so small, it's kind of like inconceivably small. We don't really have a way to get a grasp of it. So that's what I want to try and do, is look at a couple of situations to give you a feel for really how small actually are atoms. Now, keep in mind, we've got around 7 billion people living on Earth. That's a 7 with 9 zeros after it. If we're looking at a copper penny, the number of atoms of copper in one copper penny is 4 trillion times bigger. Now, trillion, that doesn't sound too bad. That sounds like something I may understand, because you may know billion and then trillion would be 3 more zeros. It sounds like it's a normal thing, but trillion is actually inconceivably large. That's a huge distance. So let's get a feel for this. What do they look like? Well, that's 7 billion written out, and that's the number of approximate atoms in a single copper penny. So we've got a lot more zeros. When we actually count them off here, we have 1, 2, 3, 4, 5, 6, 7 sets of zeros. So 29 with 21 zeros after it. Something large, so large most people don't even know how to pronounce something like that, let alone understand how big it is. So let's take a number that is big that we think we understand, a million. Can you count to a million in a semester? Now, there were, at one point in time, teachers who used to do this as a cruel joke to elementary or middle school students who thought they really knew what was going on mathematically in the world around them. Um, and maybe they were too lazy to do the work they needed to do, so the teacher could throw out, hey, count to a million, I'll give you an automatic A. So they go home and they start writing, and very quickly they get very tired. So let's take a look at it. Now, this is a type of math we're actually going to learn how to do later in the year. It's called dimensional analysis. So let's say we have $1,000. We need 1,000 of something to count. We're going to count $1,000. Now, if we could count $1 every 2 seconds, which doesn't sound like much, but think about it. 599,432, 599,433. Takes a while to say some of those things. So let's go conservative on how many dollar bills we can count in a second. Now, you know that 60 seconds in a minute, 60 minutes an hour, 24 hours in a day. To count to a million, if I had $1 million and I started counting at 2 seconds per dollar bill, it would take me 23 straight days to count the $1 million. Now, that actually makes it sound like it's doable. 23 days, that's not a problem at all. But think about it. This is 23 days where every second you never do anything but count money. There's no eating, there's no sleeping, you can't die. You can't watch TV. All you're going to do for 23 straight days is count money. Nobody can stay awake that long. So let's make it more reasonable. Let's say, okay, I've got 4 hours a night where I do nothing but watch TV or play on the computer. So I'm going to count 4 hours a day during that time block. That I can do. Well, think about it. That's then going to take you 138 days to count to a million. And that's if you have the stubbornness to stay with it and keep doing it. So even a million is an inconceivably large amount. Now let's go to a billion. At this same rate, what would a billion take? 368 years of counting money. So there's no way in my lifetime I can actually physically count a stack of $1 billion. I know we hear of billionaires, but that doesn't mean there's an accountant somewhere counting every dollar he's got. So let's go back to our penny. How long would it take everyone on Earth? Remember, there's about 7 billion people on Earth, so I'm going to get a lot of people to help me to count the atoms in a penny. Well, that's going to take me 1,764,167 years. And that's if you had everybody on Earth helping you. Nobody ever died. Nobody ever did anything but count. So the number of atoms in a penny, yes, it's big, but it's so much bigger than you possibly realize. Because honestly, big numbers, we think we get them, but we really don't. That means they must be incredibly small at a single atom. So, can we actually see an atom? Well, honestly, the answer is no. There's no way we can take, and through physical means with bending light and magnification, that we can expand that tiny little thing so much that we could physically see it with the naked eye. So there is no simple microscope that we can design that's going to magnify it enough to see a single atom. So no, we cannot, and we never have been able to see a single atom. But while we can't see them, that doesn't mean we can't sense them. And that's really the key. With a scanning electron microscope, and you can see a picture of one over here on the left, there's a probe in this really expensive piece of equipment that can actually sense the electron cloud of an individual atom. So while it can't see it, it can detect it. And it can take measurable information about it, and that measurable information can be translated to an image. So no, I am not looking at gold atoms here. I'm looking at a computer-generated image of gold atoms. And yes, the technology has gotten better. So this was actually the original picture of atoms that was released. But with a more modern technique and more modern visualization and imaging, we can get something that looks a little bit better. So these would be silicon atoms. But remember, we're not seeing the atoms, we're sensing and imaging them. Now, it wasn't long before scientists realized, well, if I can sense them, I'm interacting with them, and maybe I can manipulate them. And sure enough, they could. So you can see here, they're actually using the probe of the electron microscope to move electrons around. So these would be atoms of a certain element sitting on top of atoms of a larger element typically. Now you can see here, we've got on the left a round image where they actually put together iron atoms on a copper background. And they made a circle, the world's smallest circle. And then over here, they made it into a stadium shape. And what we're actually looking at is microstructures. This is the beginning of nanotechnology, really. If we can make these structures that are this small, these things could capture or encapsulate other atoms inside them. Now, it wasn't long before they played even more. And at one point, IBM scientists made the world's smallest sign. They spelled out the letters for IBM in xenon on a nickel background. From there, other scientists did other things. A little more modern technique here. So coming into the future, some Japanese scientists use Japanese characters to spell out atom. And these were iron atoms on a copper background. And then it wasn't long before some, I believe, IBM scientists once again now started playing with simple molecules. Carbon dioxide, carbon atom stuck to an oxygen atom. And it's actually two atoms stuck together, so it's a binary substance that's called. And they shifted these binary substances around to make the world's smallest man, carbon monoxide man. So once we had the ability to sense them, it wasn't long before we started to play and manipulate them. And that's where we are going to stop our first set of notes.